Rare earth elements, Re in brief, are the elements that are essential in our technological world, thanks to their unique magnetic, phosphorescent, catalytic, and other phenomenal properties. Growth in the use of Re was originally connected with such industries as metallurgy of special steels and alloys, missile, space, and aviation technology, organic synthesis, etc. And today, all of the miniaturization of electronics, green energy, and medical technologies, support of communications, telecommunications, and defense systems is possible only through the use of rare earth elements. In the near future, we expect a further sharp increase in re-consumption associated with the rapid development of green energy. For example, wind turbines with a capacity of more than 1 megawatt requires 1 ton of neodymium. Battery in the hybrid vehicle contains about 20 kilograms of lanthanum, etc. United States of America have identified Re as strategic elements required for civil and military technologies and for the global economy of the 21st century. Currently, more than 90% of Re to the world market supplies by China, which puts to the economic dependence all of Re consumers. In extreme conditions, this allows to manage the global Re market. China's sales policy of Re in the 1990s at dumping prices led to a worldwide curtailment of production. But then, in the second decade, China raised the prices of rare earth elements by more than 2 orders, which was a shock to the world consumers and led to awareness of their helplessness. That is why the development of the European internal resupply is critical, emphasized the European Commission. In Europe, in contrast to other regions of the world, its own raw materials in the form of primary re-minerals are completely absent. Let's consider whether there are any alternative sources of rare earth elements. In connection with the mentioned above, it is necessary to draw attention to the fact that in the European Union and in Eastern Europe associated with it, there are industrial dumps of phosphogypsum, wastes of phosphate fertilizers production from cola apatite concentrate, which contain more than 0.5% re-oxides that has commercial value. In the phosphogypsum dumps, abandoned in European Union countries and Eastern Europe, accumulated in terms of oxides from 100 to 200,000 tons of rare earth elements. Currently in Lithuania, during the production of about 430,000 tons of phosphoric acid, produced and dumped in piles more than 1.3 million tons of PG in a year, with more than 6.5 thousand tons of REO. These dumps of phosphogypsum pose serious environmental and economic problems during storage. Figure 1 shows the accumulated piles of phosphogypsum in Lithuania. Problems associated with the storage of such dumps is that they contain the impurities of sulfuric, phosphoric, and fluorosilicic acids and water-soluble salts of fluorine and phosphorus, which lead to contamination of soil and groundwater. These dumps are also sources of dust, polluting the atmosphere of the surrounding region. Furthermore, dumped phosphogypsum, due to the acidic and other contaminants therein, is not suitable for use in the production of gypsum binder directly without special washing and neutralization, which makes such distribution uneconomic. That is why these dumps lies in the amount of hundreds of million tons in the whole of Eurasia and continue to accumulate. The way out of this situation can become state preferences for processing such waste, using innovative integrated technologies for their efficient processing to obtain the sought-after products on the market. Today, in this direction emerged a group of companies of the Russian Federation, Skygrad, through its subsidiary Limited Laboratory of Innovative Technologies and Limited Saga Service. These companies are considered depleted phosphogypsum as raw material for the production of gypsum binders and Re during their passing allocation. In the case of phosphogypsum preparation technology for the production of building materials and the allocation of Re, appears a strategic source of Re raw materials, fundamentally solved the environmental problem of storage dumps of phosphogypsum, and also expanding production of construction materials. According to the proposed innovative technology for processing dumped phosphogypsum to a gypsum plaster, with an allocation of the group of rare earth concentrate, GREC, the cost of reagents and materials are less than $3 per ton of gypsum plaster, and on the allocation of 1 kilogram of REC, less than $2, which makes the proposed technology profitable and competitive. Next, we consider the proposed technology for processing dumped phosphogypsum in detail. The essence of the proposed innovative technology. Recycling of the dumped phosphogypsum is based on the innovative technology of resorption leaching from phosphogypsum pulp in an acidic solution, with the subsequent allocation of GREC from desorbate. During this process, phosphogypsum washed of contaminants, which makes it suitable for high-quality gypsum binder. Consider the basic processes of the proposed technology in the dynamic mode. Figure 2 shows the dynamic technological scheme of processing of dumped phosphogypsum with GREC allocation. The technology can be divided into 6 stages. At a first stage, phosphogypsum delivered from dumps position 10 and loaded into the hopper position 11, from where by continuous flow it enters the repulpator position 12. There, also while maintaining a certain ratio of solid-liquid in the resulting pulp, is supplied recycled water, which comes from the solid-liquid separation unit, position 3-1. Further, the formed pulp from position 2-1, pumped with a continuous flow to the sorption leaching column, position 2. At the second step is carried out sorption leaching of the Re from phosphogypsum in pulse columns position 2. For this feeds through a distribution comb a phosphogypsum pulp to the bottom of the column and strong acid cation resin. It means sorbent in H+ form from the top of the column. Sorption leaching of the Re from phosphogypsum is carried out by a counter-movement of the pulp and sorbent, respectively pulp bottom-up and sorbent top-down of the column. The sorbent, saturated with Re, is accumulated at the bottom of the column 2, and via airlift position 2-1 is unloaded to desorption column position 4, while phosphogypsum pulp, purified from impurities and Re, exits from the top of column to a solid-liquid separating unit. At the third step is carried out separation of the solid and liquid phases of the washed phosphogypsum pulp on the unit of continuous action position 3-1. For example, centrifuge, intended for separation of liquid and solid phases and washing. In this step, obtaining washed gypsum plaster position 3-3, which first accumulate in the hopper position 3-2, and then directed to produce gypsum binder and products thereof, construction dry mixtures, gypsum partition boards, plasterboard, etc. Circulating water, which is directed to the repulping stage of phosphogypsum in position 2. At the fourth step is carried out desorption of Re. For this, saturated sorbent from the column position 3 enters from above into the desorption column position 4, and the desorption solution through the distribution column continuously fed down the column 4. Desorption of Re is carried out at counter-current flow of desorption solution and sorbent, respectively solution bottom-up and sorbent top-down of the column. Sorbent liberated from Re is accumulated at the bottom of column 4 and via airlift position 4-1 unloaded in the sorbent regeneration column position 5, and desorbate solution containing rare earth elements is poured over the top of the column tube 4 in the precipitation reactor position 6. At the fifth step is carried out the sorbent regeneration for reuse. For this purpose, the washed sorbent from the column position 4 by the airlift enters the top of the regeneration column position 5, and regenerative sulfate solution through a distribution comb enters the bottom of the column. Thus, the regeneration of the sorbent is carried out in countercurrent flow of the regenerating solution and the sorbent, respectively solution bottom up and sorbent top down of the column. Ready for reuse sorbent accumulates at the bottom of the column 5 and by airlift position 5-1 unloaded in the sorption leaching column position 2, and the sulfuric acid solution is poured through the top of the column 5 into the circulation pump receiver position 5-2, and after strengthening sulfuric acid is returned to the recovery column position 5. At the sixth step is carried out an allocation of rough GRSC from desorbate and separation from the liquid phase. GRSC precipitation process is carried out in the desorbate precipitation reactors in continuous mode. To this, desorbate through the top outlets of desorption column position 4 enters the reactor position 6, which is fed of the precipitator, the carbonate salt solution. Next, the resulting GRSC suspension separated from the liquid phase in the unit of continuous action, for example a centrifuge position 6-2, with the possibility of washing the formed precipitate. At this step is obtaining revolving sulfate solution, which is recycled back to the stage of desorption of Re. Wet precipitate of rough GREC, which accumulates in the container position 6-3 and then directed to the extraction refining of impurities and the separation for group concentrates and individual rare earth compounds, obtaining master alloys with the rare earth metals, etc. Figure 3 shows the active cascade of centrifugal extractors of Limited Laboratory of Innovative Technologies (GC Skygrad) for refining and separation of GREC on group and individual rare earth elements. We have considered all the technological cycles of processing dumped phosphogypsum in the dynamic mode and saw that the proposed technology has no waste, easy to perform continuous operation, and can be easily controlled and subjected to automation. Summarizing, it can be said that the proposed innovative recycling technology of dumped phosphogypsum is environmentally friendly and competitive, has a low expense of reagents. The cost of a 99% GREC is below $2 per 1 kilogram. Implementation of the technology on an industrial scale would allow considering dumped phosphogypsum as a strategic source of raw materials, simultaneously solves the ecological problem of the storage of phosphogypsum dumps and expanding the production of raw materials resources.